Okay. Invertible matrix. Okay, right. So yeah, so we know how to find. So we discuss. Yep. So if the matrix is full rank or is non-singular, yeah, we found. Yeah, solution. Yeah, if you use MATLAB 2. Yeah, so you this is recommend. Yeah, so when you calculate, yeah, inverse of A, uh, I think it is very costly computational cost. I think high computational cost. So that's why if when A is large, so they recommend this. Yeah, use this command to find the solution, or you can use Gaussian elimination. Yep, so we discuss those things. Okay, what is so let's general matrix. Yep, so general matrix. So this is the dimension. Yeah, there are m number of rows and n number of columns. We would like to address these two things. As I said before, is there some kind of inverse? Yes, we will find that inverse. And so how can we solve this linear equation if we, yeah, so we discussed these things at the beginning of the class, right? Yeah, today's, so the beginning of this lecture, we specified our objectives and sub-objectives. Yeah, so this is one of sub-objectives. Yeah, we can find inverse for any matrix, and yeah, we discussed this one. Okay, yeah, so as I said before here, so in many practical tasks such as multiple linear regression, so these problems are arise. So how do you find the minimum x, yeah, such that this norm is minimized? Yep. So yep. So this is another objective, right? So this is the motivation. Actually, motivation, yeah, this one, and finding solutions to, yeah. So we discussed that, right? We already discussed those things, right? Okay. Okay, let me discuss, yeah, these, yeah, okay, these things. All right, start off with this. So generalize inverse. So this is a matrix, any given matrix, say dimension is how many rows and m number of rows and n number of columns. Up and real, let's stick, yeah, let's stick to real numbers. It could be, yeah, complex numbers as well. All right, let's consider this space, m cross n space, right? And G is a matrix. What is the dimension? You have to reverse this n and n. Switch these to m and n, right? So G is a matrix in this space. Yep. Right, matrix, and it is called, yeah. So generalized inverse of A whenever, so it satisfies this condition here. So A, yeah, AGH should be equal to A. Then we call G is the generalized inverse of A, right? So actually this is not unique, right? Generalized inverse is not unique. You can find any, it is not unique. That means there is no, so if A is square matrix and non-singular, then the generalized matrix would be the inverse, that inverse matrix. in that case here, if in that case G is unique. Yep. So if square and invertible, then it has only one generalized inverse, which must coincide with the ordinary inverse A. Yeah, A inverse ordinary. So you know this. But in general, so when you consider this dimension, this is a rectangle. So this is any dimension, M and N, not square, right? So according to this definition, so the generalized inverse is not unique, but it is unique whenever A is square and inverted. Okay, all right, got it. So let's so in this example here, so here look at this. So A is a matrix 1 by 2 matrix, real matrix, right? So let's find the generalized matrix, right? Inverse, let's find the generalized inverse of this A. So according to this definition, yeah, G is a matrix. You have to consider other way around. So here 1 by n. So your G is 2 by, so it has 2 rows and 1 column, right? Other way around, right? We have to switch these two M and N, right? Okay, right. Core. So if suppose G is the generalized inverse of A, then it satisfies this condition. Yeah. So so A should be equal to AGA. Okay, let's so when you plug these matrices, you will finally get this equation here. 1 is equal to, so this is a coefficient, constant. So x plus 2y, both cases you get x plus 2y is equal to 1, this one. So here x and y are parameters or variables. You can put any values, right? So that x and y satisfy this equation here. Then you can obtain infinitely many generalized inverse of this matrix A, right? So the generalized inverse is not unique, right? In general, but if you consider square matrix, that means n by n, and that your A is invertible or non-singular, then your generalized matrix coincide with the ordinary inverse, then the generalized matrix would be unique, right? But in general, it is not unique. Okay, got it? All right. So now we have a matrix. So M by N matrix, M number of rows and N number of columns. But in this so when you find the rank of this matrix, right? So when you find the rank of this matrix, you get R is so R is less than both, let's say M and N, or don't know, R could be equal to one of these M or N, right? Or less than, for instance, let's look at, so I will open, so Octave, so because here we are learning Octave, so why don't we try things with Octave? So I found some of nice matrices, which has, I think, which have so let's low rank. So oh my god, so to use my keyboard now. Yep. So CLC remove this garbage and here magic matrix magic. So I will label this matrix. I will put simple letters. Normally you have to use uppercase letters. Yep. Magic. So magic is a matrix. If you sum these rows or columns or any diagonals, you get a constant value. So that's why we call magic matrix. And if you put 6 in this way, so it has it has 6 rows and 6 columns. This is a square matrix, and let's find the rank of this matrix rank. Here you will see the rank is less than 6. So this is this is singular matrix, even though it is a square. So this is a singular matrix. So then how do you find the inverse? Generalize inverse for this. Yeah. So okay, something like that, right? So how do you find the generalized inverse? Or maybe you can type. This is a nice example. So I got to know this. Try when I prepare your assignment. So magic 8. Magic 8. So this has 8 rows and columns. So when you find the rank, so you get 3 or low rank, right? So how do you find the generalized inverse? Yep. So right, if it is low rank, right? So right, so you can permutate. So you can rearrange this matrix so that so that you get a matrix here, a block here. This block, the rank of this block is equal to R. So if you look at this matrix, 8 by 8 magic matrix, right? So we identified that the rank of this matrix is 3. So okay, then we have to identify a sub matrix here such that it has the rank of that sub matrix is equal to 3. Let's check whether the rank of this sub matrix is equal to 3. Let's check. Just check. Right. Let's check. Okay. So how do you retrieve that data? Yep. So I'm interested in this this block. Yep. So the label of the matrix is A, and row changes from what I'm interested in getting first row to third row, and from the first column to third column. So this is that block. I will label this as B, that block. So we are lucky. Let's look at the rank of this block. Rank of B. So I found that. So then you don't need to rearrange this matrix because the rank of this block is equal to rank of the entire matrix. What is the rank of this entire matrix? Which is 3, which is same with the rank of this block. If it is not, right, if you switch, if it is not, you have to rearrange the matrix so that you get something, so some block and whose rank is equal to the full rank. So no, the rank of entire matrix 8. Okay, but we are lucky here, so we get the same rank here. So this rank of this bit is equal to 3. Then look at the number of rows, and this is a square matrix, and rows, how many rows? 3. Then this is a full rank. Then this is invertible. Okay, can find inverse. Okay, then your G, the general inverse matrix would be A inverse, inverse of that block, and fill with zeros. Put all zeros in. So that is your general. So that is your G. Yeah. So that block, and you have to include. Yeah. So let me take my pen. And I choose. All right. Got it. Yeah. Okay, yep. So this block here. So when you compute the rank, we are lucky enough to get the rank of the full, rank of the entire matrix. So we don't need to rearrange this matrix. So if not, you have to rearrange, right? Rearrange so that you get something here whose rank is equal to 3, right? Yes, then the generalized matrix is the inverse of this, and you have to fill other. No, you have to interchange the dimensions. Yeah, you have to interchange dimensions. Then, so interchange dimensions and this is very. So, so look at the dimension m by n, and this one n by n. Yeah, so they pose the. Yeah, so let's look at this. You can use generalized inverse of a matrix. Of the coefficient matrix that can be used to obtain the solution to a consistent linear system. Yep, so here it is clear, right? So we know that A is equal to, what is the definition? A is equal to AGA. Yep, so let's write. So our system is, if you have, so A, oh my God, yeah, so this is, so AX, so this is, if you have consistent system, that means your B in the, column space of A. Yep, so A is equal to, so can replace that with A. Yeah, you can replace A with that. G A. Yep, so X. So which is equal to, this bit is equal to B. Yep, so this is B A G B is equal to what? B. So then, so this is your x particular, this is a particular solution to ax equal to b, right? This is a particular. So you can find many solutions. This is a particular solution. Okay. All right. To the linear system, to consistent linear system. Otherwise, you cannot talk about solutions, right? You cannot talk about solution. We already know. Yeah, let's assume this B in the set of column space, right? B is B in column space. Then this is consistent. Then we can say this system is consistent. Then we can find solution. So then what is the particular? So then when you use the definition, so then you can realize that so this is a particular solution to the system. Okay. All right. So that's that. This one now, So this is a small example here. So they consider this. This matrix, earlier matrix. So we found the rank of this matrix is 2. That means this because this is a square matrix. This is singular matrix because rank, it is not full rank, right? So this is a singular matrix. Usually we cannot find inverse, but we can find generalized inverse of this matrix, which is equal to this. It's the generalized inverse. So as I said before, generalized inverse always exists, right? Always exists. Not like ordinary inverse, right? It always exists. Okay, so this is the generalized. If the system is consistent, right, then we are able to find a particular solution. One of solutions. This is one of solutions to this system. So this is the solution. This is one of solutions to the system, consistent system. Got it? Pause the video recording. So let's look at what this projection matrix is, right? So actually projection matrix is a square matrix, right? Square matrix having this property up. So when you take the multiplication of itself, you get that itself, right? So p squared is equal to p. So why this is important, right? So let's look at our system linear. We were discussing linear system we remember from the first day we have been discussing linear system. This system. So this is the column space. If B in the column space, this is consistent. This is consistent. Yes, right. Okay. Okay, right. What am I going? So these are the examples of projection matrices, right? Zero matrix, identity matrix, and these matrices, right? These are, so if you compute this, you will see that, so so this one squared is equal to that. So the determinant of a projection matrix is either 0 or determinant of the projection matrix is either 1 or 0, right? So because of this condition, right? So So what am I going to say? Okay, so I want to say this. Yep. So this one here. All right. So this one. Let's consider. Yeah, P. So this is a projection matrix. So if I don't have time, yeah, yeah, okay, P. So this is a projection matrix P. Yep. So definitely it is a square matrix, right? And yeah, square matrix. And how many columns are there? In number of columns. And yeah, so if you label these columns up to an, these are elements in Rn space because this is a square matrix. So n elements. Okay, so if you consider the spanning set of these elements, then it is called the column space of P. Yeah, spanning set of this spanning set of these vectors, yeah, is called the column space of P. Yeah, all right. So this is the thing, right? If you consider any element in this column space, yeah, let's say this is your column space of P. So this is your column space of P. And if you consider any element, let's say this is V. V is an element in this column space of P, right? Then if you project this P with this projection matrix, if you project this V, so the then yeah, there is nothing happen. There is nothing happen. So that is the reason projection matrix is very important. Yeah. So when you project this V, so V is an element in the column space. When you project V, doesn't change. It doesn't change. It doesn't change. It remains the same. So why? So let's why is this? Yep. So let's prove this one. Yeah, because this one is in the column space, right? Okay. Yeah. Then there exists. It is in this node title. Yep. So then there exists. Yeah, some x in so n space vector space such that because because this is the range of this linear map, so there exists x in this vector space such that the projection of x is mapped to V. Because of the because this is in the range of P or column space, then there exists an element in Rn such that when you project that element, so that X map is mapped to this way. Okay. So this is X. So X is in Rn space. So this is a subspace of Rn, right? Because Rn is this is square matrix. So this one column space is a subspace of Rn. So X is any element in the space, right? So when you project this, so then this is mapped to the okay, all right. So then when you consider Yeah, so then we know, yeah, V is equal to, yep, so then let's project this one also. Right, so this is equal to, yeah, so V squared X, and yeah, so we know that P squared is P because this is a projection matrix. Px would be V. Okay. So here PV is same with V. So this remains the same. If you pick any element in the column space of P, when you project that element, it doesn't change. But when it doesn't change, it remains the same. Got it? Is that clear to you? Yeah, that is the speciality of the projection matrix. So if you consider any element in the column space of P, if you project that element, it doesn't change. It doesn't change. Get the same element. So that's the one of the properties of projection matrix. Okay. Okay. See me, we can, so here, so A is a given matrix, right? A is an M by N matrix. And this is we know that the generalized inverse always exists, right? So G is the generalized matrix of A, but look at focus just look at the dimension. Make sure that you reverse this dimension, right? M by N here, N by N. Okay. Okay. Then we can show that A times G is also projection matrix. So this is also projection matrix. So that means the column space of this, so column space of this matrix AG. So when you project any element in the column space, that does not change. Okay. Yeah, first let's prove that this is a columns projection matrix very easy. So this is the definition of generalized inverse of matrix of A, right? So this one is the definition, right? Okay. So we know that we have to show that AG squared is equal to, and first look at check whether it is a square matrix. Yes, it is a square matrix. Look at the dimension. When you multiply A and G matrices and look at the inner dimension, N is same with N, then the A times G, the dimension of AG matrix is M by N. Yeah, which is a square matrix. AG is an M by M square matrix, right? And let's check whether it is a projection matrix. Then we have to show this one is equal to itself, AG. So let's expand AG a little bit. Yeah, so AG squared is equal to AG. And according to the definition of generalized inverse, yeah, so which is, this is equal to A again. A. Yeah, so this is AG. So therefore, AG is a projection matrix. Then the column space of AG, if you consider any element in this column space, when you project this element, right, it doesn't change. It doesn't change. That is a very and other thing you can find the column space of AG. and you will realize that column space of AG is same with the column space of A. So how do you show that? Yep, so having the same column space. Yep, so yeah, very easy. Yep, so let's do that. Yep, so very. So these are so AG column space. We have to show column space of AG is same with column space of A. So let's consider any element in column space of AG. Then there exists. What is the dimension of this? So this is dimension n by n m square matrix, right? Okay. Yeah. So let's dimension. Yep. So then there exists because this is in the column space, right, of AG. Then there exists so because this is m by m, yeah, there exists some x in this space, Rm space, such that AG, yep, so AGX is equal to this one. So I think you don't need, because this is so this would be, yep, so you can show that, yeah, so the column space of AG is same with the column space of A. So this one is very useful. Yeah, then column space of AG and column space of A are the same. Yeah, so then then the column space then okay then so if you have a consistent system, that means B in the column space of, if this is consistent, then B is in the column space of A, right? So we know that this is equal to column space of AG, right? Then there exists X in Rm, because the dimension of AG is m by m, Rm, such that AGX is equal to this. Therefore, alright, so therefore, what is this? Yeah. So, so let me think, right? The column space of A is same with column space of AG, right? So we can prove that, right? Column space of A and column space of AG are the same, right? Okay. So and we show that AG is a projection matrix. Then if you have a consistent system, that means B in the column space of A, and we showed that column space of A is same with column space of AG, right? Yes. And what else? Then there exists, then there exists, then this has a solution. Yeah, there exists X such that AGX is equal to B. Yeah, this has a solution. Yeah, there exists. Yep. Then this has a solution. This has a solution. So there exists, there exists X in this space, Rm space, such that, so such that AGX, that X is equal to B, because B in the range of AG. So this makes sense. Okay, so these are very important theorems, right? So so this is a projection matrix. Yeah, if you have a projection matrix, when you project any element in the column space of that matrix, yeah, so does not, yeah, that yeah, when you project that matrix, when you project the any element in the column space of this, the outcome would be, yeah, so it doesn't change it. I mean, so this is a projection matrix, and if you consider any element in, so y is an element in the column space of AG, when you project y, it doesn't change, right? It doesn't change, it remains the same. Yeah, so these are the things you have to, yep, so understand projection matrix and yep, so generalize. If you have generalized matrix for matrix A, then AG is a projection matrix. Yeah, so then you can find a particular solution like this, because of this. Yeah, column space of A is same with column space of AG. If the system is consistent, that means your right hand side B matrix in the column space of A, and we know the column space of A is same with column space of AG. That means there exists there exists an element in our M space such that AG times X is this one. Yeah, that's the thing. Okay. Yeah, that's the thing. Like that, you have to visualize. Yeah, so now we are going to discuss pseudo inverse, right, of a given matrix, a rectangular matrix, right? So let's say B is the pseudo inverse of A, then B satisfies these four conditions here. This is the generalized matrix. So B is a generalized matrix. In addition to that, so B satisfies these three conditions, right? So B, then A is generalized inverse of B with this, right? And AB is Hermitian or symmetric because we are considering real space. Yep. So then this is symmetric. Otherwise, if you consider complex space, yeah. So this is Hermitian. Yep, AB is Hermitian and BA also Hermitian. Yep, so but here we are considering real space and AB is symmetric and BA also symmetric. So then we call B is the pseudo inverse of A, right? And look at the dimension here. Yep, so here M by N, you have to reverse the dimension, M by N. Okay. So this one is unique. Pseudo inverse is unique, but generalized inverse is not unique. Right? So pseudo inverse exists. Yeah, always exists and unique, right? Pseudo inverse of a matrix, any dimension, any rectangular matrix, always exists and is unique. So these are very important. So generalized inverse also is always exists, but it is not unique. But pseudo inverse is always so pseudo inverse always exists and it is unique, right? That's the difference between pseudo inverse and the generalized inverse. Pseudo inverse is also generalized inverse, because here look at the first property. Yeah. So B is the pseudo inverse of A, yeah, B satisfies this condition. That means B is a generalized inverse of A. But in addition to this, B should satisfy these three conditions. Then with these three conditions, B becomes a unique matrix. Will be a unique yeah. So the inverse it will be a unique matrix, yeah, with these three properties. Okay. Yeah, so the inverse is also called Pence was inverse. So only few minutes left. Yep, let's discuss. Yeah, these things. Yeah, you can go through these things now. Now you have an idea. So you have columns. Yeah, so basically we wanted to talk about solution set of this system. Now you have a broad idea about this. Why we are so this is the column space of A, and if B inside this column space of A, then this has a solution, right? Then we can find this X, right? And if B is not inside this column space of A, then this does not have a solution. Then we can find the so then B is here. Then this is the column space AX, the column space, right? Spanning set of columns of A. Yep. So then we can find X corresponding X. So this is zero identity element in this space. Yep. So So then we can find this X corresponding X such that the distance between this space and this point is minimized, right? So you have a broad idea. So that is, you have a broad idea about this AX equal B. Yeah. So, okay, let's consider a matrix. Yep. So this is a rectangular matrix. Yep. So, uh, we found the generalized inverse of that. Let's find the pseudo inverse. Yeah, so pseudo inverse, how do you find the pseudo inverse? I think our teachers will help you find the pseudo inverse. Yeah, I have no time to explain those things. Yep. So they will explain how to obtain the pseudo inverse. Yeah. Generalize, generalize, fix it. Right? So if B satisfies these two, the first two properties of the pseudo inverse, first two properties, then B is called the reflective generalized inverse of A. Okay. Yep. So if your projection matrix is symmetric, then we call that matrix is orthogonal projection matrix, right? We can show that, this one here, A dagger. So this is called dagger, pseudo inverse of A. A times A pseudo inverse of A is an orthogonal projection matrix. You can show that. So remember, if you have A, we showed that AG is projection matrix, right? This is a projection matrix, right? So now, so I will use this notation. A is dagger, right? This is called dagger. Yeah. So we know that A dagger is, yeah, this satisfies, A dagger satisfies the generalized inverse property condition, right? This satisfies, so this is a generalized inverse of A, right? Therefore, this is this is a projection matrix, right? So not only a projection matrix, but also it is symmetric because this is the pseudo inverse of A. Therefore, this matrix is orthogonal projection matrix. Okay, this one is very important. Then, if you know, so this is orthogonal projection, then you can split. Yeah, you can split. So this is a huge part, I think. So yeah, I will summarize this on pseudo-inverse. They will, I think, they will help you to find the pseudo-inverse of a given matrix A, right? So A, then you could find the generalized inverse of A. That means GA is equal to A, generalized inverse, and they will help you to find the pseudo inverse of A. Pseudo inverse, that means it is not only a generalized inverse of A, but also symmetry. Yeah, A. Yep. So but also A dagger is symmetric, and A also the generalized, so a generalized inverse of A as well as A dagger, A dagger. So, yeah, so all right. So if you are given a matrix, any dimension, any square or rectangular, so you are able to find pseudo inverse as well as the generalized inverse. So generalized inverse is not unique, but pseudo inverse is unique. Okay. And the other important one, AG is projection matrix, and A times pseudo inverse is not only projective but also orthogonal projection matrix. Okay. Okay. This is very important. Okay. All right. And yeah, so A is dimension m by n. Let's if you find the rank of A, let's assume rank of A, it could be either m or n or any number which is less than mn, or right, this one, right? So if you have a matrix, any dimension matrix, n by n matrix, right? So yeah, so then when you find the rank of A, you will get either full, this is this is column, this is row, or you will get full column rank, or you will get full row rank. So this is row rank, or some number which is less than both m and n, right? So let's say case one. Case one. So I'm going to find the pseudo inverse of this matrix, right? So how do you find that? Yeah, so case one, let's assume the rank. So this is rank of A. A is full row rank, right? Full row rank. Yeah, full row rank. Okay. All right. Yeah. So transpose. So what is the dimension of this? A n. This is m by n. Okay. So this is a square matrix. Yeah, this is a square matrix. All right. And is this invertible? Yeah. So the rank of yeah. So this is invertible. When you find the rank, yeah, you will get n, right? So therefore, this is invertible, right? This is invertible. Then a t a t inverse x. Yep. So this is identity, right? So a I rearrange this G A A T inverse. So I will take this one as a dagger. Yep, a dagger. So this is the pseudo inverse of you will show that you can show that this is the pseudo inverse of matrix A. Then, yeah, so let me check this dimension. Yep, so this is the column, this is row, and this is full column rank. This is full column rank. Yep. So this is full row rank, right? So this is full row rank. Right. Let's do the full column rank. Case 2, full column rank. So this is full row rank. So this is row. Yeah. In this case, full column rank. Coffee is column rank. Full column rank. Okay. Then, yeah, so then it transpose A. So this is n by n. This is n by n. Okay, then therefore the product of this one is m by m, and because the rank of this one is m, therefore this is invertible. Then yeah, a t a, yep. So yeah, a t a inverse. So this one exists. Yeah. So this is identity. Yeah. When you rearrange this, yeah. Therefore, this you can show that. Yeah. This is the yeah pseudo inverse in the document. Yeah. So yeah. Here we go. So this is full. Yeah. So this is full column rank. Here column. This is column. My column. So this is my column number. Column number. Column number. This is row number. So this is full row rank. So pseudo inverse would be this, and this is full row column rank, and pseudo inverse would be this, And the projection matrix, if you write the projection matrix, I will write in a different color. So projection matrix would be, I think this. This is pseudo-inverse projection matrix would be, for this one, projection matrix would be, yeah, AG is the projection matrix. Yeah. Remember, yeah, so this one is the projection matrix. Yeah, projection matrix. Orthogonal projection, not only projection, it is orthogonal projection. Orthogonal projection. So yeah, this is the projection matrix. Yeah, these are very important. Yeah, so for this one, yeah, this is the projection matrix. A dagger. Yep, so which is A. Yeah, so this one is the projection matrix. Yeah. This one, no, other way around. Yes. A projection matrix is this. Because this is symmetric, I think. Yep. So A, D, A, A, D, inverse A. Yeah, this is the projection matrix. Orthogonal projection. Yes. Orthogonal projection. Other way here. Similarly. Onto row space of A. Yeah, so this is project onto row space. Let me check. Yeah, this is row number. Yeah, row number. Yeah, this is full row rank. Yeah, so this is project onto row space of A. Yeah, so yeah, like that you can access you can practice these things with with MATLAB or Octave, right? Here we go. Yeah, orthogonal projection matrix. Yep. So how do you find the pseudo inverse of? I think they will help you to find that. Yeah. So in summary, yep. So and the other case, so case one, yep. So case one, so this rank could be M. Yeah, we discussed that M. Rank of A could be N. Yeah, so we discussed that. What if the rank of A is something less than M and N? So in that case, how do you find the pseudo inverse? Yeah, then you have to use this as we do. Yeah, this is called uh, singular value decomposition, I think. So I think they will explain this to you. So right. So yeah, there are three cases, right? So the rank of A, when you find the rank of A, it could be M, N, or something less than M and N, right? So if it is equal to M, if the rank of A is equal to M, how do you find the pseudo inverse? Yep. M, yeah, so then this is full row rank. No, M is column. Yeah. this is full row. Yeah, A, the rank of A is full column rank. Yeah, so then yeah, so then this the rank, yeah, so this rank of this matrix is also n, therefore this is invertible. And from this one, yeah, so you can identify the pseudo inverse. This is the pseudo inverse in that case. And the other case, when the rank of A is n, and yeah, so then what is the dimension of this one? N by n. Therefore, this is invertible. This is invertible. Then you can find the pseudo inverse. Yeah, this is the pseudo inverse. Okay. And what if the rank of A is less than m and n? So then you had to use so there's I think I don't have much time to explain that. I think you need time to discuss everything. We have the time to cover these things up. So yeah, SVD. Yeah, so SVD. Yeah, let's type. So SVD help. SVD. Yeah, you can learn about that method if you refer to this note here. It is called singular value decomposition. It's defined by this relation here. So you have to use this decomposition to compute the pseudo inverse when the rank of A is something less. Yeah. So when you find the rank of A, you get some number which is less than both m and n. So then in that case, you have to use SVD decomposition to compute. Yeah, so this is the pseudo inverse. So I'm not going to prove that to this time constraint, right? We just use this octave to compute pseudo inverse of that. I think our teachers will explain those things the next session. Yeah, so I hope I cover. All right, so there's a built-in function in MATLAB Octave. Yep, so called pseudo inverse. If you want to find pseudo inverse, yep, help pseudo inverse, P inverse. Yes, yep. So here we go. Yeah. So yeah. So yeah, you can also call them Penrose. Yeah. Penrose or pseudo inverse of this matrix X. So you can use this built-in function to find the pseudo inverse of a matrix. So I think we have discussed these things earlier. Another important case, yeah. So, right. So this theorem is very important. Where's that? Where's that theorem? Yes, yeah. So minimize of the this one. No. Yeah, this one here. Yep. So okay, this one is very important when it comes to your assignment. Yep. So we already know that x could be any it's a set of variables, so variable vector. So this is an element in column space. We know that when you change x, you get different points in the space, right? In the column space, right? So So how do you find the optimal x? Optimal value if the system is consistent. So, is the solution of the least square, not that one. Is this one? So, is this the theorem I'm mentioning? Yeah, here we go. This one. So I think, yeah. So this one is very important. Yeah. So I think I will give a problem. I think for your exam, I think, yeah, this one is a nice, but so we didn't have time to do it. So I think to cover this. So earlier I mentioned this theorem. Yep. So we find the minimum distance between this space and this point if the system is inconsistent, right? So how do you find that minimum? Yeah. So distance. How do you find the corresponding x? Yeah, so this is very important theorem. So using pseudo inverse, yeah. So this solution is unique. Yeah, this is a unique solution. X star is the unique. So this is a unique solution. So yeah, so this one gives you the minimum distance between this space and the point B, right? Yeah, this theorem is very important. Yep, so try to understand. I think I discussed already at the beginning of this lecture, right? So yeah, this is the corresponding x here. Okay? So this when you consider this length, you get the minimum distance. You get the minimum length. You get the minimum when you compute. So this I will put x star here. When you compute this, when you compute this norm, right? This norm, you get them. So this norm would be. So this is x star. Now this is your x star. X star. X star would be x star is a dagger, the pseudo inverse of a times b, right? Okay. And when you compute the distance, yeah, this is the minimum distance between this space, column space, and point. This vector, this vector. So this is very important when it comes to your exam, right? I think I use this one for your assignment. Yeah, this theorem here. So if this is a consistent system, so this is for inconsistent system, right? Inconsistent system. Yeah, so if your system is consistent, right, then yeah, this one is the exact. So we can show, yeah, so we showed that, yeah, this is the exact solution to this. And having the minimum, yeah, norm. Yeah, so when you compute the norm of this solution, we know that this is so yeah, so you get a minimum norm. So and the other solutions to this, you will get yeah, get much large than this norm, yeah, for other solutions. So this is the optimal solution. Optimal means, yep, so when you consider the distance between x star and 0, yeah, which is this, yep. Yeah, distance between these two is the minimum. Yeah, this one, a dagger pseudo inverse time b for this system. Yeah, this is a solution to this. So you have many solutions when this is a low rank matrix, right? Let's say A is a matrix layer. So if the rank of this matrix is low, then you could find infinitely many solutions. But this one, so this is a particular solution. When you compute the norm of this solution, you get a minimum value. But for other solutions, the norms of other solution would be larger than this. Yeah. So this is the thing. It's related to inconsistent system of no, this is consistent system. Yeah, that's why I'm talking about solutions here. Exact solution to this. So this is not a this one, right? Yeah, this one is the minimum distance. Yeah, we are talking about this problem. This one minimum x of this norm, right? So we are finding, yeah, so x such that, yeah, such that this norm is minimized. So that means, in other words, we find the minimum distance between this b and this space. So what is the minimum distance between these to this point and this space? Yeah, so then how do you find that corresponding x? Yeah, so for this x, you have this distance. For this x, yeah, so this is x. When you change x, you have this much. But a particular x here, this x, you have minimum distance. Yeah, this is minimized. This norm is minimized. So this length, the length between this space and this point is minimum for this x star. Yeah, so we started our lectures by discussing discussing the system of linear equations. So we had this system, right? Ax equal b, right? Okay, so there are two types of systems, consistent and inconsistent, right? Consistent mean so this is an element of column space of A, right? So I hope you understood that part, right? Column space of A, right? So this is an element of column space of A, right? If this element is equal to B, yeah, that means B is in the set of or space of column space of A. So let's draw the column space. Yep. So let me draw the column space. So this is my column space of A. So B lies on this in this plane. Let's say this plane represents the column space. Yeah, column space of A, right? So if B in on this plane, so then we can find. So here this is the zero element, and these are the columns. Columns of A, first column, second column, and let's say this is nth column, and the spanning set of these column is called column space of A, which is a subspace of let's say A is n by m, right? This is a subspace of Rn, right? Okay. If B is an element in Rn, right? There are two possible cases. B lies in the plane, or B is outside of the plane, right? There are two possible cases. If B in this B, so the space contain B, yeah, B can, yeah, so if P lies in this plane, then we call that system is consistent, right? Then we are able to find the solution, here. So this is the corresponding x, AX. So this is the solution here. Okay. Okay. But that depends on this matrix A. A could be, so here we know that A could be singular and singular and non-singular. If A is non-singular, we can find only one solution. If A is singular, we could find infinitely many solutions, right? Infinitely many solutions, right? Because of that, we could, if A is singular, right, we could find infinitely many solutions to this system. Then which one is the optimal solution out of? Optimal means optimal in the sense that the norm of this, the norm. So which one is the optimal solution to this system, right? Yeah, optimal one would be A dagger times B, I think. According to the theorem, optimal would be, check up, so yeah, A dagger times B, optimal one. Pseudo inverse of A times B, which is the optimal one, right? A could be any. A could be singular or non-singular. If it is singular, yeah, so this is the optimal. No, singular in this case because we could find infinitely many, right, solutions. There are infinitely many. So this is the optimal one out of those infinitely many solutions, right? So which one? Yeah, A dagger times B. Yeah, this is, yeah, so this would be the optimal solution according to this theorem, right? Okay. Now let's discuss the other case. If the B is located outside of this space, this is your column space of A. Now B is located outside the space. Now here we have, yep, so A1 and everything, this is 0, A1, A2 up to AM, right? And this is the spanning set of these columns, and this is called column space of A. Then, yep, so now you can change X, right? You can change this X. Now we know that the system is inconsistent, right? That means no solutions, right? Ax is equal to B. No, you cannot find solution. But you can compute this Ax. What is this? Ax minus B. This is norm, right? This is the distance between this point and point on the space, or a point in the space, right? So what is this? This one is the distance between these 2 points. Which points? B and points in the space. Got it? The minimum of this. How do you find the optimal X? So we are going to minimum of this X. These are not solutions, right? X. Yeah, when you change X, yeah, so you get different points in the space. Okay, yep. So from this, according to this diagram, yeah, this is the minimum distance perpendicular. This is the projection, orthogonal projection. Yeah, projection. I drop a perpendicular to this place. If let's assume this is a plane, right? Yep. So then, what is the corresponding x? The corresponding x would be, I will denote x star, and the corresponding x would be according to this theorem. Yes, yeah. Here we go. Again, A dagger B. Got it? Pseudo inverse of A times B. Did you understand now? I summarize